All right, good morning, Distant Learners. Hopefully you're doing well. It's good to have you on stream today. We have Grace and Jake here. Make sure anyone else throws their name in the chat. Why isn't Jaylene just doing video? Text her, tell her to say get on the video, you lazy bum. I'm just kidding. All right, we are going to start today. Hopefully you were able to finish your homework last night. Jake, you already sent it to me. Grace, I think you already turned it in, so I think that's everybody. But make sure you guys turn in your homework if you have not already. The verses 4 times each. Yeah, sometimes you do forget what that is, Emma. Sometimes you do forget what that is. I'm not wrong. I'm going to give you guys about 5 minutes today, not as long as yesterday, to work on that booklet. Most of you probably should have finished most of it yesterday. Some of you that maybe came in later didn't get to finish everything. Maybe you did. I know it's not too much, but today will probably be the last day I give you time in class. And then we're going to kind of expound on the thief and the robbery yesterday. We were talking about the sheepfold and everything. We're going to go more on that and reading in John chapter 10 today. But again, we're working on that student work for about 5 minutes, and we'll be back to continue with our lesson. Let me know if you have any questions. And again, we'll be back soon. What's been going on in John chapter 9 and 10? Make sure all electronics are put away. What have we been reading? What did we talk about yesterday? What did we begin reading yesterday? What's kind of going on? Okay, I mean, yes, we did talk about sheep and the sheepfold. Okay, but why? Why is this being talked about? Why is Jesus quoting this in chapter 10? Where was he at the end of chapter 9? What was going on? You guys remember? Okay, he's talking to the Pharisees saying what? What was our first person we talked about? The blind sinner. Okay, talking to the Pharisees saying, hey, you guys can't see. Okay, obviously most of them probably could physically see. Okay, they studied, so they probably had to be able to see since they were considered the smart part of the Sanhedrin. Okay, scholars, people that read and studied the Old Testament. Okay, so we see physically they could see, but Jesus was saying, hey, no, you're not blind physically, you're blind spiritually. Okay, but Jesus used kind of like a reverse psychology. He said, hey, until you are truly blind, what? You won't see. So then they stated, well, we must be blind then. We must be blind because we can see. They're like, we can see, we know the scriptures, okay, we can physically see, we must be blind then. Blind in your reference, Jesus. Okay, but obviously they weren't, because being blind was not a physical blindness, but it's basically saying, hey, you rely not on yourself, but on who? I know it's early, guys. I know it's early, but they're not hard questions. Okay, to not rely on ourselves, but who? To rely on God or Jesus. Okay, we see Jesus telling that, which brought us to chapter 10 in verse 1. It says, verily, verily, I say unto you, he that entereth not by the door into the sheepfold or fold, but climbeth up some other way, the same is a thief and a robber. And we started talking about a little bit about that yesterday. We talked about the sheepfold. Okay, we talked about, I didn't have this up there, but we talked about how it was a place of shelter. Okay, in its physical description, the purpose of the sheepfold was to shelter them. Okay, whether it's storming, okay, to give them a place of rest where they would have the shepherd or doorkeeper to watch over them. Okay, we talked about that yesterday. Okay, that's the purpose of the sheepfold. Okay, we mentioned the word porter, meaning, again, that doorkeeper. Okay, but today, we're gonna kind of define, again, at the end of the verse, it says, the same, but climbeth up some other way, so not going in the entrance of the sheepfold or door. A person that climbeth up another way, the same is a thief and a robber. So I have a question for you. If you guys were going to your house, right? Okay, say you get home from school, whether you drove yourself, you get picked up, whatever. Okay, you go to school, Ellie, she walks there. Okay, you go to school, you go home, and what do? How do you get inside your house?
I break the window.
No, you don't. Okay, if you have a key, which probably most of you have, whether it's in the back, or you know the back's unlocked, so you just go to the back, or you have a garage door opener, so you go through the garage, or you have a key, or you know someone's home, so you knock. Someone does one of those, okay? We're not breaking windows. And if you do, I'm sure your parents would kill you every single time. You'd be like killed 1,000 times by now. Okay? But we see usually, common sense, you enter the what? The door. You all came into this classroom this morning. Some of you might be here physically, but not here mentally yet. Your mind's still catching up. Okay? But we see you guys came to school, and though sadly we cannot face through walls, although that'd be awesome. But we can't face through walls. We're not Doctor Strange or Vision. Okay, sorry, that's just not how it works. Okay, you came through a what? Noah, a door. Okay, so let's say you go to your house, okay, or you come to someone else's house. You just show up to their house. You're like, oh, okay, let's go inside. And while we're opening the door, Christian, just like he said, he just goes to a window and starts climbing through the window. Or let's say you show up to your house and someone's just climbing in your window. It's like, well, that's not right. Right? If someone's just walking through your door, you'd be like, oh, must have a guest over, maybe a family friend, a relative, someone's here. But if someone's climbing through your window, you're like, what in the world is going on? Maybe you're calling 911. Maybe you're the brave soul that's going to charge in and be like, what are you doing? Confronting them. Okay, so we're going to see this definition of an obvious thief. Right? We see someone doing that and we're like, okay, that is not right. Something's going on. Okay, someone breaking into my house, Okay, all the things that would go through our mind. Okay, but what is the definition of a thief? Okay, it is one who breaks into a house to steal. Okay, the reason why they're not going through a door is because what? They don't want to be.
They don't know how to pick locks.
Okay, maybe. Okay, maybe they don't know how to pick lock. They're a bad thief. Okay, or a lazy thief. Okay, make sure our chair's down. Sorry, Emma. Okay, but we see, okay, when they don't go through a door, okay, it's because they're trying to break into something suspiciously to also maybe find something else to take. Okay, so we see it is one who breaks into a house. Remember, they don't go through the door. They go a different way, just like we saw in verse 1 of chapter 10. He climbeth up another way. Okay, secondly, we see usually they enter somewhere other than the door. They don't want to be seen, right? In any cartoon, you see like the thief is in the shadows going like this, looking behind his shoulder every single time. Okay, looking if people are watching, trying to be in the shadows. Okay, so we see this thief. You would begin explaining why you were doing a suspicious thing. If someone caught you doing that, like if we come to school, or if I came to school in the morning and Noah is just trying to open the window from the outside and climb in, I'd be like, what in the world are you doing, Noah? I'd be like, what are you doing? I'm sure some of you maybe have, but I'd be like, Noah, what are you doing? Just go ask the teacher for a key if it's locked, or just go in the door, right? Like, Noah, what are you doing? Okay, and we see that that's going on. Okay, we see again this in chapter 10, verse 1, talking about this door, and then talking about this thief, the one that climbeth up another way. Okay, we're going to see this apply, this being an example. Okay, Christ doesn't just say a thief and robber in this analogy, in this illustration, for no reason. Okay, every time Jesus is talking, it's for a reason. There's either a hidden meaning or a very blunt meaning. Okay, and we're going to talk about kind of the meaning of this thief and robber in verse 1, and we're going to read a few more verses today. Okay, but you see, because Christ is the door, we know that. Okay, we've read that. We've seen it. It says in verse 7, chapter 10, then said Jesus unto them again, verily, verily, I say unto you, I am the, what? You guys have your Bibles open? Make sure our phones and everything are put away. Okay, I am the what? In verse 7, chapter 10. The door. I am the door. We see Christ is the door. Everyone who tries to get to heaven by any other way must be a thief and a robber. Verse 1 said that. It exactly says, but climbeth up some other way. Okay, so if we know, as we've talked about throughout this whole year, and some of you probably already knew this, okay, and maybe we're just learning a new thought. Okay, Christ is the way. It says he's the bread of life. Okay, he's the living water, and we've talked about so many different things, right? Now he is the door, so we know he's the only way. We know that. Okay, but we see this thief and robber trying to go a different way. Okay, but the thing is, to heaven, we know it's only through Christ. This statement by Christ was a clear and definite accusation that the Pharisees were not truly spiritual. If they had been spiritual, they would have come to God through God's door, right? For how smart they were. If they truly were spiritual, as Christ said, hey, you must be blind, saying, hey, you have to have faith and trust in me. If they truly were spiritual, they would have done that. But they weren't. They had faith in who? The Pharisees. Who did the Pharisees have? The law or themselves? Good, Michelle. They had faith in the law or themselves. Okay, and we see that happening. Okay, we may apply this truth to every false cult or religion. But let's briefly see how it applies to the following well-known, or some well-known religions, okay, that we know today. Okay, and they're up there on the screen already. We see Buddhists. Okay, what do they seek? They seek nirvana, which is what? A mindset of peace, basically. You could go into it, okay, a type of enlightenment, okay, if you want to say that. Okay, but we've heard about nirvana a little bit. It's basically like this world and a mindset of just peace and tranquility, where nothing's wrong. Everything's okay. Okay, and we see this in Buddhists. Okay, we also see the extinction of desire. Okay, Buddhists believe 4 noble truths: the existence that involves suffering, that the cause of suffering is desire, that release from suffering comes only by ending desire, and that they can attain nirvana because of all this. The extinction of desire following by the eightfold path of enlightenment. This eightfold middle path involves right understanding, right mindedness, right speech, right action, right living, right effort, right attentiveness, and right concentration. After following this path of works, they believe that they obtain, like I already said, nirvana. Okay? Nothingness. Again, it's all just peaceful. There's nothing there. Okay? Absolute nothingness, where I'm all alone, safe, peace and quiet. Okay, that's what the Buddhists believe. They find their nirvana or their salvation through what? What did we just say? Basically through just like thinking and doing right. Okay, they find that through that. Okay, we also see Hindus. Hindus also seek a type of nirvana. They believe, however, that nirvana is the ultimate reunion with Brahman, which is the reality or the impersonal force in the universe. Okay, the person they're seeking. This goal is achieved when they believe through a continuous cycle of birth, life, death, and rebirth called what? What is when you die or you're born? There it is. Reincarnation. Okay, respawn. Man, a society of too many video games. But reincarnation. As soon as an animal, an insect, or a person dies, they say it immediately is reborn into another form. Okay, that's what they believe, and most of you probably already know that. It moves up or down to the scale of life. The direction depends on the quality of life that it has lived. This law of reaping in the next life, the harvest of one's life, is called the law of karma. And it explains why Hindus will not kill a cow or some insects or even a rat, because it might be who? Could be grandma, could be your brother, could be your sister. Okay, it could be anyone in your family, so that's why they don't do that. Okay, so they do these things, these actions, because why? They're seeking their state of nirvana, their salvation. Even though this practice poses grave problems for sanitation and public health, again, they are trying to climb up, like the Bible said, they're trying to climb up some other way. Okay, rather than just believing in God's door, the door that God sent, that lived here on earth, that died for us, that rose again from the grave. Instead of accepting that, they're like, no, we're just going to try to find a different way to find salvation, right? To be able to go to our nirvana or their type of heaven. Okay, we're just going to find a different way. We're going to climb up some other way. Okay, we see Muslims. Muslims are those who practice the teachings of Islam. They seek a paradise of wine, women, and songs. They believe that they can achieve this goal by abstaining from these very things here on earth. They will be rewarded with them in paradise. So they abstain from things that might be considered worldly, like a lot of alcohol, okay, a lot of doing immoral things with women, because they're doing it literally, or abstaining from it here on earth, because they believe if they abstain from it here on earth, that they'll achieve it in the afterlife, in their next life. Hey, I'll be rewarded with the things that I'm abstaining from. Does that even make any sense? Man, I don't know about you guys, but that doesn't even make any sense. They will be rewarded with these things in paradise. In addition, they must obey what is known as the 5 pillars of Islam. Okay, the recitation of the creed. Okay, there is no God but Allah, and Muhammad is his prophet. That's what they will quote and recite. Making at least one pilgrimage to Mecca. Giving money to the poor. Praying 5 times a day and keeping the fast of the month of Ramadan, which is actually what some people are doing today, right now, at this moment. Okay, main reason why I know that is because there's a basketball player in the NBA that has become very annoying on social media, but he's doing that right now. Okay, and he's telling people, hey, respect me, respect what I'm doing. Okay, many of the Islamic terrorists who have attacked the United States were reported to have been living sensual lifestyles. In the months leading up to their crimes, some believed that they were motivated to commit mass murder because they were convinced the only way to atone for their sin was to give their lives in a holy war. People that maybe had done bad their whole life, now they're like, hey, I want to achieve that afterlife. I want to be able to have all these things that I've been missing out on, or the things that I was supposed to abstain from. I want to still have all the good enjoyments of life after I'm dead. So what did they do? They said, hey, I'm just going to kill a lot of people, because that's what their religion teaches. Okay, to sacrifice themselves for a holy cause. Interestingly, none of these religions seek the true God or come to God by the way of the door. They are all considered, as we see in chapter 10 and verse 1, as robbers and thieves. Okay, maybe some of us aren't Buddhists or Hindus or Muslims. Okay, we're not quite that extreme, right? But some of us might be guilty of this crime. That we try to get to heaven some other way. Right? Again, at this point in your life, certainly if you've been in this school for a while, whether through chapels or through Bible class or even this year, okay, you know what the Bible says. You've heard it. You've memorized it. Okay, whether it's for a quiz, for a test, okay, you've heard it spoken on through maybe church or through Bible class, again, maybe chapels, okay, maybe from your parents. Okay, so many different sources you might have heard the Bible. And we clearly see in chapter 9 and chapter 10, it says basically this: hey, this is the way, and if you don't take this way, you're known as and we're talking about right now, a thief and a robber. Because you're trying to climb up some other way. Whether it's, hey, I'm going to be good, right? We can do good things and I can be a good person. Okay, maybe I'll go to church, right? I've heard going to church is good. I'll go there. Okay, that's good, right? I'm a good person if I go to church. I'll obey my parents. I've heard the Bible say something like obey your parents because that's the right thing to do. So I'll do that. Even if it's hard, I'll do that. Okay, I'll make sure I'm good in school for the most part. I'm kind to my friends. Okay, I believe in God. Like, I think there is a God. He created me. So I'll listen to him. When the Bible's open, I'll respect him some. Okay, but if we have not accepted the door and entered through the door, all that stuff's worthless. Now, we might not be mass murdering people for holy wars. We might not be worshiping or trying to attain this state of nirvana. Okay, but if we deny the door, we're just as guilty. Isn't that crazy? You're like, well, Mr. Cora, I'm not that crazy. Right? I believe in all the things you're saying, but have you trusted for yourself? See, you can come to a Christian school, you can go to a nice church, you can do anything. You can associate yourself with the right people all the time. But if you haven't accepted for yourself what the Bible teaches, it doesn't mean anything. I can't accept it for Christian. I can't accept it for anyone. Your parents can't accept it for you. It's not what your parents do or believe. Okay, your brother and sister can't accept it for you. You have to accept it for yourself. Okay, we see this, the Bible talking about this thief and robbers. We see different examples through that through different religions. Okay, but it doesn't have to be another religion. It can just be someone that says, hey, I am a Christian, right? So many celebrities today say, hey, I'm a Christian. Now, does that mean they are or aren't? No. Some of them maybe. Maybe they don't have or know the whole Bible, so they don't live like it all the time. But they could still be saved. Okay, maybe some say it because of a platform, right? We have that through politics and different things as well. Okay, but it doesn't matter what they say or what they do. It only matters what you believe in your heart. Okay, mind, you knowing things is just knowledge. But me believing things, man, that's faith. That's what the Bible says we're supposed to have. Okay, and we see some things, and tomorrow we're going to talk about how we can do that. Who do we do that through? Okay, obviously we know it's Jesus. We know he's known at this door, but we're going to talk about a few more things tomorrow. Okay, but we're just going to end off reading through the Bible in chapter 10, kind of starting again in verse 1 and read a few more verses, and then we'll be done for today. Again, it says, Verily, verily, I say unto you, he that entereth not by the door into the sheepfold, but climbeth up some other way, the same is a thief and a robber. But he that entereth in by the door is the shepherd of the sheep. To him the porter openeth, and the sheep hear his voice. And he calleth his own sheep by name, and leadeth them out. And when he putteth forth his own sheep, he goeth before them. And the sheep follow him, for they know his voice. And a stranger will not follow, but will flee from him, for they know not the voice of a stranger. This parable spake Jesus unto them, but they understood not what things they were which he spake unto them. Then said Jesus unto them, so he gives them, again, this passage we just talked about before. Okay, talking about the sheepfold, talking about this porter, the doorkeeper. Okay, talking about how if you try to climb up some other way, you're known as this thief and robber. And then Jesus is like, hey, you don't understand this? Hopefully you can understand this now. In verse 7, Verily, verily, I say unto you, I am the door of the sheep. The sheep being who? Who's the sheep representing? Us, people. Right? Sometimes something tough comes in our life and we go astray. What did I say yesterday a shepherd does when his sheep go away? He has a staff and he directs them back to the flock. Now does the sheep go away? He's like, all right, just leave that one alone. I'm going to leave that one over there. He's a loser. He never listens. I'm just going to give up on him. Is that what shepherds do? No. There's actually an example in the Bible. Okay, you guys have probably heard the story or the parable where the shepherd leaves his 99 and goes saves the what? The one. And that's what Jesus is for us. No matter how dumb we are, okay, no matter how lazy we are, no matter how difficult we can be in listening, okay, God is just waiting for us. He's right there trying to direct us back to him. He's not forcing us. He's not grabbing our neck and get back here. No, he's just gently guiding us back with his guiding hand. Okay, in verse 8, all that ever came before me are thieves and robbers, but the sheep did not hear them. Again, saying in verse 9, I am the door. By me, if any man enter in, he shall be saved, and shall go in and out and find pasture. And we'll end verse 10, as those are our memory verses for this week. The thief cometh not, but for to steal, and to kill, and to destroy. I am come that they might have life, and that they might have it more abundantly. Okay, again, talking about thieves and robbers, these different religions, or like we said, it could just be people that we believe, but we don't believe. We know, but we don't have faith. We're just as guilty as the worst of them, if that's how we think, if that's how we are. Okay, and Jesus says again in verse 9, as our memory verse is, I am the door. If any man enter in, if you come into the door, if you believe through me, he shall be what in verse 9? Hopefully we're reviewing that because that's our memory verse for the week. He shall be what? Saved. It can't be any more clear than that. I don't know how these Pharisees just didn't understand this man has done all these things. Okay, he has told them specifically who he was, what he was there for. He said, hey, you believe in me and you will be saved. You walk through the door, you are saved. I am the door. Okay, but we see a group of people. Be careful, because we see a group of people. These were smart people. They knew a lot. But we see all of them deny. They deny the door. They deny Christ. They try to kill him. Be careful, because we could become one of those people. We could know all these things. We could hear all these things. We could go be successful in life. But if we deny the door, what is it all worth? The Bible says all our works are but filthy rags. It won't mean anything in the end. Everything here on earth, whether we enjoy it or not, okay, I'm not saying you can't enjoy life. That's not what God says. But if we are doing life without him, what's the purpose of it? Do it for him. Have joy through him. Okay, and we'll see that you can have joy more abundantly. Okay, that's it for today. We won't have any homework tonight. Okay, hopefully the girls can have a good trip and good volleyball game as they're going to be leaving early. But no homework tonight for you guys. Okay, we'll have economics. We'll probably be reviewing for a quiz later. But that is it for today. Distant learners, let me know if you have any questions. We'll see you in a little bit. All right, welcome, listeners. Hope you're doing well. We are going to pray during this hour. Sorry, I forgot to do that last class. But we're going to pray before this class. We're just going to finish the few notes we have, and then we are going to watch a video. Sorry, I can't play it for you guys, but I will be playing it for the class. So I'll just be, we'll go through these notes quickly. I'm going to show the video, and then I'll be back in about 10 minutes after showing the video to review for our quiz tomorrow. But we will go through the notes first. Are there any prayer requests today? Prayer requests. Yes, ma'am. Unspoken for Kylie. Help the volleyball team as you guys are now leaving in just 1 hour. About 1 hour you're going to be leaving. So hopefully you can get some rest or whatever you need in the vans or car. With that, bless them with safety in the games. Actually, 2 games. We got back-to-back games, so bless them with that. Any other prayer requests? Yes, ma'am. Unspoken. Tori has an unspoken as well. All right, pray for spring formal. And then last question is there any volunteers that would like to pray for us today? Or must I call on someone? Anyone? Any soul wants to pray for us today? Doesn't mean you can't pray again? Do you not like praying that much? Oh, wow. Wow. All right, Ian, can you pray for us today? Thanks, man. Amen. All right, thanks for doing that, Ian. Again, we're just going to go through these real quick, so pull out your notes. Your homework was already due. If it's not turned in, it's not good. Okay, but make sure you get it turned in. You probably won't receive full credit if it's turned in after this. Okay, but we will finish the notes quickly, so have those out. We're just going to go through them. Okay, I'll read them out, and then we will watch a video that's talking about some of the things here. Okay, first we have geographic specialization. This is the production of goods in which a country or region has absolute or comparative advantage. Okay, obviously we talked about those advantages yesterday. Make sure our phones are put away. If you can't stay off your phone, put it out where I can see it, or else I will take it. Okay, but we talked about the advantages yesterday. Hopefully we can remember those. Okay, this is just talking about where it's located, which country it's happening in. Okay, next term we have protectionism. This is the theory or belief that domestic manufacturers need government protection against foreign competitors. Okay, basically if we're in the United States, okay, the protectionism is basically saying, hey, if we take something from China or whatever, okay, we want to be able to do it within ourselves first, okay? The rights of our people first before we give it to everyone else. That's why people get very angry when jobs or anything are given to other people, jobs that are here in America before Americans. Some people have gotten very mad because of that. Okay, probably the 2 things that our video is going to talk about most is protectionism and free trade. Okay, this is whenever there are no restrictions or penalties placed upon the trading of goods. Okay, that means there's no taxes, no, again, like it says, restrictions, no rules. Okay, basically you do whatever you deem is right. Okay, in our last term in the notes, there should be tariffs. Tariffs are basically, and we've learned this term before, are just the taxes that must be paid on imported goods before they're allowed to enter an area. Okay, we should know that one already. We've learned it before. Okay, but that is it for the notes. Again, listeners, we'll be back in about 8 to 10 minutes. Okay, we're going to watch a video here in class, and then we'll be back to review for our quiz over Chapter 7 in a little bit. Okay, welcome back. Hopefully you're still here. Okay, but we are going to review for our quiz at this time. Okay, the quiz is going to be over. Okay, specifically pages 111 to 117. Okay, so basically the notes from, there's like one or two from a couple days from last week, but mainly just from yesterday and today. That's what it's covering. Okay, so I have questions like this. This should be an easy one. Okay, easy 3 points. What are the three components of mass production? Okay, there's a few different terms you could use for a couple of them. But what are the three main components of mass production? We talked about these. What's the first one? Division of labor, or it could also be called specialization. Okay, meaning what people are good at. Okay, division of labor. What's another one? Standardized parts, straight from the notes. Good. And last one? Okay, you could say two different things, but the easy one would be assembly line. Okay, you can put assembly line, or you can put automatic conveyance. You can do that as well, but assembly line would probably be a lot easier for that. Okay, those are the three things. Those are three easy points to get. Do not miss those ones. Okay, you will need to know the difference between absolute and comparative advantage. We talked about both yesterday. Okay, we mentioned again something that kind of tied them together today. You just want to know the difference between the two. What is the difference? What's absolute advantage? Okay, basically they have the ability or the access to one product, right? And they're the best at that one product. That's absolute advantage. Okay, we're talking about like one entity, okay, between their competitors. So if like me and Ellie, if Ellie, like the example we watched in the video, if she did pictures and I did pizza, okay, I would have absolute advantage in the pizza. Okay, whether I had it working because of the money I'm spending and the money I'm getting, okay, all that stuff. Okay, what is comparative advantage? Okay, there's a key word. Remember, we talked about comparative advantage is a key word. Okay, something that makes a difference. What are you saying, Noah? There's the term. Yep. Opportunity cost is the word you're looking for. But yes, perfect example. Okay, definition. Okay, it's the ability of an entity to produce a good or to provide a service at an opportunity cost that is lower than your competitor. Okay, what term refers to the result when specialization is carried beyond the point of maximum efficiency? I'm going to say it again. Okay, I'm not repeating every question. Okay, but this one's a little bit longer. We talked about it today. What term refers to the result when specialization is carried beyond the point of maximum efficiency? Okay, so we have specialization. Basically, what is specialization when it's carried beyond? It's common sense. Even if you weren't taught this note, you could put it together. Okay, so if something was less than, we could say it was under the bar, right? If something's beyond or more than, it's specialization, but what kind? I just gave you it's under or above is not the right word, but you're getting closer. Wrong direction now. Okay, it's not literal. Okay, specialization when it's beyond. It's over specialization. Over. Okay, you're on the right direction. Wrong term. Okay, over specialization. It is a term that refers to the result when specialization is carried beyond the point of maximum efficiency. Okay, it's over specialization. Okay, by using mass production, Henry Ford was able to reduce the total cost of production. True or false? The word you're looking at is total costs. By using mass production, Henry Ford was able to reduce, this would be from your reading in the homework, was able to reduce the total cost of production. True or false? It's not true because Michelle already said that. What is it though? It's not total cost, it's what? Oh man. Can't give you all the answers. Okay, you'll want to go look that one up. It is a little common sense as well. Okay, there are some questions giving kind of examples. I'm going to give you one of them. Okay, it's like this. If David can mow 10 lawns or rake 6 yards, in the same time it takes Peter to mow 6 lawns and rake 5 yards, David has the absolute advantage. True or false? Okay, it's a longer question. You're probably like, I don't even know what you just said. Okay, so basically you just need to know the difference between what two things? Absolute advantage and comparative. Okay, if you know those two things, you should be able to get 2 questions in the short answer and 2 questions for the true and false. What? What is he in both? In both. David can mow 10 lawns and rake 6 yards when Peter can mow 6 lawns and rake 5 yards. Who has the absolute advantage? Okay, and that you're just putting true and false. Should be really easy. Okay, there's another one just like that right under it. Okay, with the true and false, giving another example. Those should be really easy if you know the definition of those words. Okay, that is your quiz. That is it. Okay, there's about 10 questions. It should be really easy. The main things, again, you want to know 3 components. That's 3 points, so you want to know those. And the difference between absolute advantage and comparative advantage. Okay, if you know those like 5 things, you should be able to do great on the quiz. Okay, any questions? Okay, I won't give you guys any homework tonight. Kind of help the volleyball team out with that. But we will have that quiz, so make sure you review for that. There is no Bible homework or economics homework other than studying. Discipliners, let me know if you have any questions. But that is it for class. We will see you guys tomorrow.
Wrong screen. All right, welcome to. I accidentally put up the chapel announcement. Anyway, because I have my scene, and then right underneath are all the ones we don't use often. Because I've put mine all the way at the bottom, so people leave it alone. Because I got annoyed by people like moving around the camera, and I'm like, just leave it in the corner where I put the thing, and then make your slides where there's nothing in that corner. Moving on. I'm not better. All right, so go ahead and get out your textbooks. We're on page 289. We're starting 17.2. We're talking about nuclear stability.
We never finished.
We finished 17.1. Uh-huh. You want to keep going with this?
We didn't.
We did.
Oh, no, we did. Wait.
I know. This is the last slide of 17.1.
Oh, I thought it started on this page. That's my bad.
Yeah, it is. All right, anyway. Let's go ahead and get going here. A tremendous variety of unstable nuclides are known. In fact, only 264 of the 3,000 or so nuclides that occur in nature or have been synthesized in the laboratory are stable. The stability of any atom is determined by the number and arrangements of protons and neutrons in its nucleus. About 99.97% of the mass of an atom is contained in the nucleus. On a practical level, this means that when you lift a 50-pound weight, you are lifting 49.99 pounds of atomic nuclei and only a quarter ounce of electrons. However, the nucleus is minuscule compared to the atom as a whole. In fact, if the nucleus were the size of a marble, the atom would be the size of a large sports stadium. Okay? So picture a marble on the center of a 50-yard line in a stadium. There's your model of an atom. Okay? And yeah, that's, yep. As far as volume. It has been estimated that the total volume of an atom is at least 1 trillion times greater than the volume of its nucleus. If 99.97% of an atom's mass is contained within 1 trillionth of its volume, the matter in the nucleus must be extremely dense. Calculations reveal that the density of an atomic nucleus is about 2.8 times 10 to the 14th grams per centimeter cubed, 25 trillion times denser than lead. A 12-ounce soda can full of solid nuclear material would weigh well over 100 billion tons and would contain the same amount of matter as a solid lead block, 1.3 miles on a side. You can see a picture of what the size of the block we're talking about. I think that's the skyline of New York City in front of it. Okay? That's the level of what we're talking about, okay, for the same density. Page 290. Atoms at ordinary densities must consist of mostly empty space. Okay? So matter is mostly empty. Okay? And that's not an oversimplification. It is vastly free space. So the question is, why don't we go through things more? Like, this wall. Okay? Because the electrons are repelling each other. You actually can't touch anything. This is one of my... this is the thing we get more into in physics, but you actually can't physically make contact with anything, including like people, like tables. Like y'all are like touching stuff to like prove me wrong. You're not actually touching it. What's happening is the electrons in your hand are repelling the electrons in the surface at a subatomic level.
I'm going to tell that to my mom next time we
Anyway, yeah. Anyway, so yeah. Okay. Anyway. For all intents and purposes, though, when we say we're touching, like, you know what I mean, okay? Technically, you're not even touching your clothes. I mean, that's just how atoms work. There are parts of yourself that never touch other parts of yourself. Like, yeah, you never touch the ground. You're always levitating. It just doesn't feel like it. Basically, all that is what's happening at the core. Obviously, that's a gross oversimplification, and things like that. But that's the reason is the negative charges are repelling each other. That's why you can't just walk through walls.
So if I make myself positive, if I thought positive...
Then you would be stuck to the wall and unable to move, and then that would be a whole different problem. All right, moving on. Moving on. All right. Silence. If two electrically charged objects are brought close together, they attract each other if their charges are opposite, but repel each other if their charges are alike, either both positive or both negative. This force increases exponentially as the objects are brought closer together. For this reason, two protons in close proximity will repel each other because both are positively charged. At the minuscule distances in the nucleus, this repulsion becomes unbelievably strong Two protons 10 to the negative 15th centimeters apart, which I can't even fathom how tiny that number is, repel each other with an electrostatic force of roughly 2.5 million newtons. In units we understand here in the U.S., over 500,000 pounds of force. This repulsion is some 10 to the 36 times stronger than the gravitational attraction between the protons. The surprising strength of that repulsion between protons leads to an important question: what holds the nucleus together? Because it's where all the positive charge is. So what's holding that thing together? Well, we discussed quark theory, but there's more to it than that. So the answer is that there's another force at work, and that's the strong nuclear force. This is an attractive force in the nucleus about 10 times stronger than the repulsion of the like charges within. There's argument over whether or not this is its own force or whether it's just due to quarks. If you just arrange all the charges correctly, it's fine. That actually is a prevailing theory due to nuclear research and things like that. But again, this whole science is about 100 years old. Like, we're trying, but like we can only go so fast. So it's gone faster than any previous scientific discoveries, let's put it that way. So there's still a lot we don't know. But for now, the working theory is that there's a strong nuclear force that acts on protons and neutrons. This force has an exceedingly short range, only 1/4 of a meter. But within that distance, it is 100 times stronger than the electromagnetic force by which protons repel each other. Because of its strength, this strong nuclear force is able to overcome the natural repulsion between protons and bind them together into a stable unit. There's a reason why we call it the strong force, because it's strong. Okay, it's the strongest one. It is the strongest force that we have studied. As in, this is a thing you should know.
So you're telling us this is a term?
Yes. All right.
That'll be strong.
I know, in a big shock to everyone, that the strong force is strong, but you know, what you can do. All right, moving on. Despite the immense strength of the nuclear force, not all arrangements of neutrons and protons are stable. Unstable nuclides tend to undergo nuclear reactions that convert into other nuclides. This conversion of one nuclide into another in a spontaneous nuclear reaction is called radioactive decay. Radioactive decay is almost always accompanied by the emission of, nuclear radiation. Oops. The strong nuclear force, along with the other forces of nature, is an important part of God's design for the universe. The Bible tells us that Jesus Christ, the Creator, is upholding all things by the word of his power. You see that here in Hebrews 1:3, who being in the brightness of his glory and in the express image of his person, and upholding all things by the word of his power, when he had by himself purged our sins, sat down on the right hand of the majesty on high. The writer of Hebrews, Paul, his personal opinion there. It's just written like Paul's writing. What do you want me to do? Where was I going with this?
Great question. I don't know.
No, the whole Paul thing. Anyway, moving on. Whoever's writing this is just kind of going through the description of Jesus Christ and his power and kind of his pedigree, if you will. And in passing, he mentions he upholds all things by the word of his power. Like, he's the reason the whole universe exists. All right, and moving on. And it's like, what? Okay. Because to God, it's such a nothing. Okay. And that by him all things consist, because he was before all things. Okay, in Colossians 1:17. Although science can tell us some things about the forces and laws that God has governed or established to govern the universe, we know from the scriptures that it is ultimately God's power that sustains his creation. We see this in John 1 as well. Okay, by him were all things were made, and all things were made for him. Okay, and so that's really, as much as I really want to get into it, but just mentioning that there is, yeah, there's a lot going on here that we don't even understand, but of course God does, because he made it all. But now we need to get into a whole different thing. Modern measuring equipment has allowed scientists to determine the masses of individual subatomic particles with great accuracy. You can see that on table 17.1 on the same page as that picture. If you add the masses of 8 protons, 8 neutrons, and 8 electrons, you'll find that they have a total mass of 16.131921 atomic units. However, if these same 24 particles are assembled together into a single atom, the atom they form, oxygen-16, has a mass of only 15.994915 atomic units. The math doesn't check out. And this is weird. So weird, it has a name. Somehow, 0.137006 atomic units of mass disappears, quote unquote, when the particles are assembled together into an oxygen atom. This surprising phenomenon is not confined to oxygen-16. The mass of every atom is measurably less than the total mass of its individual particles. Now, we know from mathematics the sum is equal to all its parts, except in nuclear chemistry. Yeah. The sum is less than the whole is less than the sum of all its parts. And it's super weird and it's super trippy. And we call this phenomenon the nuclear mass defect. Where does the missing mass go since all 24 particles are still present? The answer lies in the work of brilliant Jewish physicist Albert Einstein. The nuclear mass defect is a straightforward consequence of Einstein's theory of relativity. One of the most famous equations in all of modern science is E equals mc squared, which can be written as energy is equal to mass times the speed of light squared. This is why. This is the only time this equation actually matters. Okay, it actually bothers me that this equation is in such pop culture because it looks so simple. But this equation really is what blew nuclear chemistry, blew nuclear chemistry like wide open as a field of study. I'm sorry, that was a horrible pun. All right, anyway. Wow. All right, anyway. Okay, but this equation here, it's actually a simplified form. This is actually not the full equation. The full equation is actually much longer. But the simplified form is that we can take mass and convert it to energy. We can take energy and convert it to mass. We've talked before in this class about the conservation of matter. We've talked in physics about conservation of energy, or will talk in physics, depending on which cycle you're on. The truth is, they're one and the same. They're directly proportional. Matter and energy can neither be created nor destroyed, only changed from one form to another. It is possible for energy to be converted completely to mass. It's possible for mass to be converted completely to energy, which is both astounding and terrifying at the same time. Because mathematically speaking, there is very little distinction between mass and energy. So what happens is, or one consequence of this mathematical relationship is that we can regard energy as having mass, which is just trippy. Any quantity of energy has an associated mass of that energy divided by the speed of light squared. Now, normally it's so tiny we don't see it. But according to this interpretation, when an object gains energy, it gains mass. When an object loses energy, it loses mass. So technically, you are slightly heavier when you're going down the freeway at 90 miles an hour versus right now. You're not going to notice it on a scale. Okay? But like, technically that's what's happening. Very little. You would weigh a whole lot less. But anyway, whole different thing. All right, different discussion. Yeah, just ever so slightly. All right, moving on. Just don't move. Okay, now that's horrible. All right, moving on. We're done. All right, now, the equivalent mass of 1 joule of energy is approximately 1.1 times 10 to the negative 17th kilograms, or about 6.7 times 10 to the 9th atomic units. When 8 protons, neutrons, and electrons are assembled into an oxygen-16 atom, they make it sound like Lego, but moving on. Approximately 2 times 10 to the negative 11th joules of energy is released as heat and electromagnetic waves. The mass of this amount of energy is 0.137006 atomic units, precisely equal to the missing mass. The missing mass got released as energy. Because it's more stable, it takes less energy to hold it together than it is for them to exist apart. So when you account for that, we get a balanced equation. Whoops. Great. Thank you. Yes, I wanted to immediately scroll back to chapter 15. I love digital textbooks.
Me too.
Actually, most of the time they're great. It's just moments like that where it's like, I was in the middle of a point. I wasn't like going. Cool, thanks. All right, anyway. Measurable mass defects also occur in other types of nuclear reactions. For example, the decay of an atom uranium-238 into thorium-234 and helium releases 7.5 times 10 to the negative 13th joules of energy, which is equivalent to a mass of 0.005 atomic units. Comparing masses, we find that the decay products are indeed 0.005 atomic mass units lighter than the original atom, corresponding to the amount of energy released. When you're dealing with subatomic particles, you have to start considering the mass that energy itself has. It's weird. Okay?
Wait, so if I electrocute someone, do they weigh more?
I mean, both more and less, because, when they start to burn. Moving on.
Yeah. But like if I
All right. Since matter can be converted into energy and energy into matter, the law of... there we go. Moving on. In nuclear reactions, energy does not appear out of nowhere. Instead, matter is converted into energy. That's how nuclear power plants work. We are literally taking matter and turning it into pure energy. Kind of. Moving on. The law of conservation of matter and energy is thus obeyed. Nuclear binding energy. The nuclear mass defect is the equivalent of the energy released in the hypothetical formation of a nucleus from its parts. The reverse is also true. The mass defect is also equal in magnitude to the energy required to separate a nucleus into individual neutrons, protons, and electrons. For this reason, the energy equivalent of the mass defect may also be called the nuclear binding energy. We may define nuclear binding energy as the amount of energy necessary to break up a nucleus into its component nucleons. Since energy must be supplied to a nucleus to break it up, a nucleus must have less energy than the individual component nucleons. The energy difference is equal to the binding energy. Yeah. I'm working on it. There. I want this. I forgot this was here. The problem with PDF is you can't insert videos into them.
Oh yeah.
And this is PDF slides.
That's an issue. Have you thought about
Not doing PDF slides? Yeah, but then I have to do math in other languages. Why is my website not responding?
great question. Maybe it's because you turned it off. Your Raspberry Pi back home.
I mean, that could actually be a problem.
You might want to ask your wife to go check.
Well, that's fun. Okay, I'll fix that later.
Go ahead and just go check out.
No, it's not something she can check. All right, so
She can turn it off and turn it
no, you don't. Moving on. I think it's the USB cable I have plugged into the Raspberry. My whole web server is a Raspberry Pi.
on. Yeah.
Yeah, the whole thing runs off an SD card. It shouldn't work, but it does. Anyway, so look at the bottom of page 291. Basically, all it shows is that if we take individual particles, shove them together, they're going to lose energy and come together into an atomic nucleus. If we supply energy to an atomic nucleus, we can break it apart into the individual components. Okay, that's all I was going into. All right, moving on. Electron volts. When dealing with individual atoms and molecules, the joule is an inconveniently large unit of energy. Detonating a single molecule of TNT, for example, releases only 6 quintillionths of a joule, and we're just like, okay, we don't want to deal with this. Okay? We gave atomic mass its own unit for a reason. Okay, let's give it its own energy unit, because seriously. That's basically what's happening here. So, a more convenient unit on the atomic scale is the electron volt, defined as the kinetic energy gained by an electron when it is accelerated through 1 volt of electrical potential. This has nothing to do with actual volts. It's just part of its definition, hence the name. Okay? So it doesn't mean it's how many volts a thing has. It means how much energy an electron would gain given a volt of electric potential. Does that make sense?
What?
Yeah. Okay. Anyway. No, not watts. Watts are a different unit. I'm sorry, I had to. Anyway, so they're not actually increasing the voltages of these things. Basically what's happening is we know how much energy an electron gains when we supply it 1 volt. That's the amount of energy in 1 electron volt.
What?
No, watts are different. We've been over this. All right, so the thing you need to know For example, in a cathode ray tube connected to a 1,000 volt power source, each electron emitted by the cathode would strike the anode with 1,000 electric volts of kinetic energy. Okay, it's how fast it'll go at that voltage. The relationship between joules and electric volts is on the screen. The detonation of TNT, of a molecule of TNT, produces about 35.6 electron volts of energy. Okay, much more manageable unit. When we start having multiple molecules, that's when we want to go to joules. Okay, so we can go back and forth. Since nuclear reactions produce far more energy than ordinary chemical reactions, the energy of nuclear processes is often expressed in mega electron volts, because why not? Where 1 mega electron volt is 10 to the 6 electron volts, because that's what the prefix mega means million. Okay. Since mass and energy are related by equation 17.1, we may also obtain a relationship between megavolt and atomic mass unit. 1 atomic mass unit is worth 931.5 mega electron volts.
Oh, sorry.
So if you were to take a proton, okay, proton-ish, and able to convert it entirely to energy, that's how much energy you would get out of it. Which is actually kind of a lot from 1 proton. It's still less than a joule, but compared to the size of a proton, it's a lot. All right, moving on. Let me see here. The more strongly a nucleus is held together, the more energy will be required to separate the individual nucleons, and the higher the binding energy. Since overall nuclear binding energies are also affected by the number of particles in the nucleus, a more meaningful quantity for comparing nuclei is binding energy per nucleon. Again, the higher this is, the more strongly the nucleus is held together. This quantity is found by dividing the binding energy by the number of nucleons in the nucleus. So we know how much energy is released whenever something is formed. And so that's how we figure this out. A plot of binding energy per nucleon against mass number reveals that the binding energy per nucleon increases rapidly for light elements, but that the increase is not as rapid for elements after carbon-12. Thus, the strength of the interaction between nucleons appears to increase rapidly until the region of carbon-12, whereupon the addition of more nucleons has much less effect on increasing the binding energy. A maximum strength of interaction between nucleons occurs in the region of iron-56, as shown by a maximum in the curve. Okay? Iron-56 is the most strongly held together element, okay, per nucleon. After that, it starts to go down. You see, binding energy per nucleon and thus nuclear stability can be increased for heavy elements such as uranium by splitting them into lighter nuclei, a process known as fission. Such a splitting results in lighter nuclei that have greater binding energy per nucleon. On the other hand, the binding energy per nucleon for the lighter elements could be increased by combining combining into heavier nuclei. Such a process is known as fusion. We will study fission and fusion in more detail in section 17.5. In either case, large amounts of energy are released because of the changes in the binding energy that occur. All right, so let me walk through this just a little bit, and then we'll probably be done, because I don't know that I want to go into the next section today. We'll see. Actually, no, I may want to start it because it's long. Anyway, let's look at this chart for a minute, though. Okay? Notice that toward the right is uranium. Okay? Specifically, uranium-238 is the rightmost element on this graph. Okay? There's also uranium-235 right before it, but uranium-238 is the interesting one. Okay? The whole point of fission, the whole reason why uranium elements start to fall apart is because they can get into a more stable position by becoming smaller things. Specifically, by getting to lead, they can get super stable. On the other side of the graph, you have hydrogen. Hydrogen is barely held by anything at all. When they mash together, they get to helium, which is more stable. The sun is a fission reactor. No, fusion reactor. I always get the two mixed up. Okay. The sun is a fusion reactor. Two hydrogens will smash together and form a helium ion. That's what happens in the sun. It's a giant nuclear reactor. We know that its fuel is about half spent, assuming the star was originally pure hydrogen. Now, probably not, but okay. We know it has about half of it already converted. So what that means then is if it were to run out of hydrogen and only have helium left, the reaction would cease. We're actually right about in the prime range for there to be a supernova with our sun within the next 5,000 years. Like, it's got a while. All right. Because we know that stars either will burn themselves out, or when there's about half fuel left, a chain reaction will get set off, and the whole star will just go at once. That's really the two options. So, anyway, that's the reason for it. But yeah, the sun is a nuclear reactor. It's just, contained and very far away from here. And at that point, you're really thankful sound doesn't travel through a vacuum, because all our eardrums would burst if it could for even half a second. Because the sun is loud. Oh yeah. That's exactly what we're doing. Yeah, fusion reactors are basically making mini stars on the planet. Not super dangerous or concerning at all, but it's actually also really cool, and we'll talk about it more later on. Fission, on the other hand, is taking an element and either forcing it to break apart earlier than it normally would, or just reaping the benefits of that happening and enjoying the energy that's coming off of it. Basically is the idea. You don't want to stand too close to it, but that's the idea there. Either way, energy gets released because things are getting more stable the closer we get to iron 56. All right, does that make sense? Okay, so that's the reason for both reactions. We need to get into nuclear reactions in general, though. So, 15.3, 17.3. Never mind. That jumped to chapter 15 messed with me.
Again?
No, it just... When I was trying to scroll down on the page, but I was too far to the right, so it grabbed a scroll bar instead.
Why don't you just grab the scroll bar again?
That's... yeah. All right. And just as chemical reactions may be described by chemical equations, nuclear reactions may be described by nuclear equations. They're the same thing, guys. They just have some extra notation. All right. Showing the atoms or particles that react in the products they form. For example, the formation of oxygen-16 from its individual particles could be written as examples 17.4. When working with nuclear equations, keep in mind that nuclear reactions we shall study will follow two important rules. Rule number 1, the mass number must be conserved. You have to have the same amount of mass before and after each equation, because physics and conservation. We good? Okay? If not, you're literally breaking the universe, and that's bad. All right? It's one thing to break math. It's another thing to break the universe. Okay? So, please keep them balanced. The sum of the mass numbers of the reactants must equal the sum of the mass numbers of the products. In other words, the total number of nucleons on both sides of the equation must be the same. Second of all, the nuclear charge or atomic number must be conserved. The sum of atomic numbers of the reactants must equal the sum of the atomic numbers of the products. For beta decay, this rule requires treating the electron as having an atomic number of -1. Okay? You notice electrons are represented with an atomic number of -1. What's happening there is, again, a neutron is basically breaking apart into an electron and a proton. That is an oversimplification, but that's essentially what's happening. Okay? Good? A lot of this is going to be oversimplification because nuclear chemistry. All right, so just there's my disclaimer, okay, of this is not going to be fully in depth.
You just don't want to teach how to make nukes, be honest.
Well, there's that. All right. We shall see these rules demonstrated and observed as we continue our study of nuclear reactions. Just real quick note, we've seen some of this notation before, but let me walk through it just to make sure that we're good. We still have 8 protons. Okay, let me get, there's a way to get, there we go, laser pointer. All right, so we still put a number in front to represent how many of things. So we have 8 protons. Notice the positive charge here. Okay, and then notice we have 1/1. The top number is your atomic mass number. Okay, so it's how many total protons and neutrons. Obviously, it's 1 because it's a proton. Follow me. Okay, the bottom number is the atomic number. A single proton has an atomic number of 1 because, hydrogen. That's what it is. Okay, make sense? So far, so good. Neutrons have the symbol of 1, 0. They have mass but no charge. So they do not contribute to the identity of an element. They can contribute to the identity of an isotope, but that's only through mass. All right, makes sense? Finally, electrons, negative charge, also -1 atomic number. Again, that's kind of a... We're kind of fudging it, but like at the same time, it's kind of what happens. So like, there it is. Finally, we end up with oxygen. Okay, so in this case, we have 16 total particles in the nucleus, 8 protons. It is neutral because we have 8 electrons and 8 protons. Does that make sense? And then plus energy. The energy may be left off occasionally, or quite a bit, but just keep in mind it's always there, especially when we're dealing with nuclear reactions. All right, make sense? Cool. Now, whenever an atomic nucleus breaks up or changes, emitting radiation, it is said to have undergone nuclear decay or radioactive decay. Early researchers quickly discovered that not all radioactive decay is the same. Rather, there are 2 main types of radioactive decay, designated alpha and beta decay, which is a high-speed electron. Either type of decay may also involve the emission of high-energy electromagnetic waves called gamma rays, and some other types of nuclear radiation may also involve the emission of high-speed neutrons, known as neutron radiation. Okay? So those are 4 types of radiation. There are 2 types of decay in there, alpha and beta decay. The other 2 types are just energy. Well, okay, no, the one has particles, but like, moving on. All right. Trying to draw lines here is not super effective. All right, but before trying to get into differentiating those, I'm going to save that part for tomorrow. That's where I'm going to leave off today. We'll pick up tomorrow with the types of nuclear decay. I just don't want to start that without being able to finish it. So, distance learners, I'll see you guys later. Don't forget, guys, quiz Friday over 17.1 to 17.3. Yeah. All right, there we go. Oh, sorry. That yeah was apparently really loud. All right, we're on page 348. Page 348, we're finishing up 7.4, properties of logarithms. The last property we need to learn is how to change bases of a log. They go through deriving the formula. I don't care. Okay, here's the formula. To change bases, you simply divide it over itself. I did type something wrong.
You did type something wrong. It's a log over a different log.
Can I have 5 points extra credit in this class?
No,
In this
I found it.
In this class.
You know what? Yeah, sure.
He owes me extra credit in lunch as well.
All right. So if you have a log and you're trying to get to a different base, you simply take the log of the thing and then the log of the base.
Wait, aren't they the same bases?
No.
Oh, okay, now I understand.
Yeah. So in other words, if I'm going to take and try to find the log 3 of 20, okay, all I got to do is I can just use the calculator on the button.
Nice.
The button on the calculator, shush, by default does base 10, right? Okay. There's no way to fill in your own base, so it's really easy though. All we do then is do log 20 base 10 over log 3. You could do the same thing with natural log, by the way. It would work just fine. So if you just type log 20, divide it by log 3, you get the same thing as the log 3 of 20.
Divided by log 3.
Yeah. Where's my scientific calculator?
Oh, okay.
I found one the other day.
Wait, isn't that just no, that's expanding. But expanding is just subtracting, right? No?
Huh?
Is expanding-
Oh, right. No, I'm just going to use Desmos's. Desmos has a...
Wait,
Desmos.com/scientific will actually give you a scientific calculator.
seriously?
Yeah.
Wait, so
So if I do this, okay, for log 3 of 20, all I'm going to do is I'm going to type function log of 20, close my parentheses, divided by the log of 3. They don't let you change the base on here, do they? I'm just curious. No. Okay. Anyway, but that gives you the change of base, which is about 2.7-ish in there. All right? You use however many digits they tell you in the directions. If you did natural log, you would get the same thing. Actually, here, I'll prove it real quick. Natural log of 20 divided by natural log of 3. Is that a 3? No, I typed the wrong button. There you go. See? Answers are identical. Huh? Why? If you want that answer, oh, that would be super helpful, actually. Hey, there we go. Dark mode and everything. Right?
oh my goodness.
It's amazing how much of a difference that makes. Anyway, the reason that works is shown on page 348 if you want to see how they got there. I don't. That's the derivation of the change of base formula.
Derivation? Don't you mean derivation?
No, I mean derivation. That's how you pronounce it. Anyway, but I'm not getting into it in this class because I don't care. 10 out of 10 teaching. All right. Where's my cursor? There we go.
Why do you
That's right.
cursing back?
All right. Can we go to where PowerPoint's the active window again? Can we do that? Thank you. All right. Condense and evaluate 2 log 3 of 8 and minus 5 log 3 of 2. Because we can change bases, it's usually more convenient for things to be in a single log statement. So that's what we're going to do. That's why it says to condense, then evaluate, because we want to condense first, obviously. So keep in mind this means we have the log of 3, 8 squared, minus the log of 3, 2 to the 5th. Okay, then we have the log of base 3 of 64 minus the log of 3, okay, 2, 4, 8, 16, 2. Yes, it's components in my head. All right, you just count by the number. It's not that hard. Anyway, or no, you keep multiplying, whatever, moving on. All right, subtraction means we can divide, so log of 3 then of 64 over 32, which means then we have the log base 3 of 2, which means then I can plug this in to the calculator as the log of 2 divided by the log of 3. And we get about 0.631, which is the correct answer. Make sense?
Wait, okay. So so if I were to take, if I need to change two different logs, right? Okay, like two bases from two different logs, right? And I need to switch one to another, and I need to do it on a calculator, right? So do I do log? Let's say I need to switch it to the base to 6, right? And since it's the base is
Why not just set both of them to the base 10 and then you're done?
Can you do that?
Yeah. All right. Homework. Rest of it, quiz tomorrow.
All right.
Bye, Jaden.